In this video, we're going to be talking about why does water boil at different temperatures depending on your altitude. So basically, let's say if we're at sea level or ground level, and let's say these are some water molecules. Turns out that the boiling point water at this ground level is 100 degrees Celsius. Now, if we go to like a peak of a mountain, for example, very high up, turns out that the boiling point is actually going to be less than 100 degrees Celsius. And let's find out why that is. So just to simplify things here, I have two containers, let's just say, and they're filled with the same amount of water molecules. And before we start kind of talking about this, we actually have to talk about what boiling even is. And before we start talking about what boiling even is, we have to know about something called vapor pressure. So vapor pressure is the pressure exerted by the molecules of a liquid as they escape into the gas phase, and represents the tendency of molecules in the liquid to evaporate. So let's say if I have a container and it's filled with water. All right. So evaporation is basically, let's say we have liquid water. All right, so this is liquid water. And evaporation is just when kind of molecules of liquid water have enough energy to actually escape and turn into a gas. All right. So when, molecules are going from a liquid to a gas, well, that's evaporation. And evaporation happens at any temperature. All right. So that's one important thing to know. Evaporation can happen at any temperature. It just turns out that when things are hotter, so it just turns out that, if let's say this container is super hot, a lot of water molecules are going to evaporate. And when things are colder, not as many water molecules are going to evaporate. When the container is at a higher temperature or when it's hotter, evaporation is at a higher rate. When it's colder, it happens at a lower rate. But, when it's cold, it still happens. And the reason why things evaporate at a higher rate, well, it turns out that, let's just say these are two water molecules. There's something known as intermolecular forces, or we'll just call them IMFs. Intermolecular forces, which are basically forces of attraction between two molecules. So these two water molecules actually attract each other. I'm not going to go into too much detail about that, but they're basically attracted to each other. And basically, if things are hotter, what happens is that water molecules move around quicker. So when it's hotter, water molecules move around quicker, and that means that if they move around quicker, well, they're more likely to kind of escape this force of attraction. They're more likely to break this force of attraction, making them go into a gas phase. A liquid is a state of matter where the molecules are close together, but they're not in fixed positions like a solid. So they're attracted to each other, but they're able to kind of slide past one another. However, if you break the attractions between the water molecules, then that's when you become a gas. All right, that's when that thing becomes a gas, when you're able to break all of these forces of attractions. Now, water molecules, right? Let's say if they're in a fixed container. Let's say if they're in a container. I can actually measure how much pressure the water molecules are exerting on the container. Because think about it, right? Evaporation happens at any temperature, and let's say this right over here is liquid water. So when some of the liquid water evaporates, they're going to hit this container, and that's going to exert a pressure on this container. And that's something known as vapor pressure, basically, right? And it turns out that the hotter, the container is, well, more molecules are going to evaporate. Therefore, more molecules are going to hit the wall, and it's going to lead to a higher vapor pressure. If it's colder, not as many molecules are able to evaporate and hit the wall. Therefore, the vapor pressure is lower. So vapor pressure gives insight on the tendency of molecules in the liquid to evaporate. Now, the thing that prevents this liquid water from instantly boiling is atmospheric pressure. Basically, at the ground level, there's also air, right? So at sea level or, at ground level, there's also air molecules up here, right? And they're exerting a pressure downwards, right? They're going to the container and they're exerting a pressure downwards. Now, boiling happens when your vapor pressure, so when the when the amount of evaporation, right, that exerts like a pressure on your container. And it turns out that when the vapor pressure is equal to the atmospheric pressure, that's when boiling happens. You can think about all of this like atmospheric pressure. You can think about it as sort of cock blocking like all of the water molecules from escaping. The air molecules in the atmosphere basically exert a pressure on this surface of a liquid, okay? So it exerts pressure on the surface of a liquid, and that affects the ability for the gas molecules to escape. And this atmospheric pressure is what the liquid has to overcome for the molecules to go into the gas phase, or for, the water to start boiling. So not only does the water molecules need enough energy to break these forces of attraction, but they also need enough energy to kind of counteract the atmospheric pressure. It turns out that 100 degrees Celsius, the vapor pressure of the water molecules is equal to the atmospheric pressure. And when the vapor pressure is equal to the atmospheric pressure, this is when the water molecules start boiling, okay? So boiling is just when the vapor pressure is equal to the atmospheric pressure, and this is how kind of bubbles are formed when you see something boil. Whenever you see water boiling, you see bubbles, right? So let's say I draw like a little bubble here. That basically represents kind of air pockets of water vapor. So right inside these bubbles right over here, there's water vapor. And then when the bubble pops, then the water vapor escapes into the air, like so. It turns out that the atmospheric pressure is going to be way less. It's going to be way less than what you had at the ground level. And the reason why is because, think about it, you're high up at a mountain. So there's going to be less air molecules, right? Think about the higher you go, the less molecules you have. Think about like going to space, for example. There's barely any air particles in space, right? So the higher you go, there's going to be less air particles you have. And in addition, at the peak of a mountain, it's going to be pretty cold. So the air molecules aren't going to be moving as fast, meaning that the atmospheric pressure is going to be lower, right? If the air molecules aren't moving as fast, they're moving really, really slowly, they're going to exert a lower pressure. They're not as effective as, stopping these water molecules from escaping. Therefore, it's going to take less heat in order for the water molecules to escape. So at a peak of a mountain, it's going to take less heat for the water molecules to escape because, well, there's less atmospheric pressure sort of holding the water molecules back. So therefore, it's able to boil at a lower temperature because there's less pressure put on the water molecules in the first place at the peak of a mountain.